So going here from this demo, this is where we're going to start. So what I have is I have a laser. I can take this laser, I can point it down at my paper. As I point the laser, you see the laser moving around. I also have this thing. It doesn't look like anything much. You can look through it. Stuff goes through it. Light goes through it. But what this is called a diffraction grating. And what I can do is I can take this laser, shine it at one point, and then also make it so that way the light is going to go through this diffraction grating. And as the light goes through it, I get something else to happen. It takes the laser and makes more laser beams. I can see that it really makes a good number. And depending on how I hold this, it changes how these beams appear. I can make a lot of beams. I can rotate them. So what we're seeing is from this laser, we get a laser light to be made. The laser light goes through this diffraction grating, and it creates something known as this diffraction interference pattern. So this is what we're looking at. So I like that. This actually was thought to be sort of magic at some point in time. So I like that we're saying in here, some of us are saying that this looks like magic, but it's not really magic at all. We're going to get into what it is and how it is. So getting back over to here. I want you to draw what you saw from that demonstration. So I have here a laser, a diffraction grating, and a wall. I want you to finish this to try to draw what you saw. So now we have an idea of what we saw. We have it drawn out, what we actually see. What I want you to try to do is I want you to put it on here. Now, there's no right or wrong answer for what you think. But what I want you to try to do is tell me why you think this is. What do you see going on, and why do you think this is happening? I'm gonna give you guys another 10 seconds to try to say why you think. So I got some pretty cool comments in here. So some people are even telling me that they're thinking that it's light bouncing around the paper, reflecting back around. Some other people are saying that it could be making other lasers. Some people are also saying that it looks like it could split the laser. Some people are saying that diffraction sounds like what happens with a rainbow, where it bends light. So that's very similar. And it's very similar in the fact that a rainbow is made by a thing called refraction, not diffraction. So refraction, that's because light in air travels at a different speed than light in water. And so that's why rainbows happen, because, well, light goes at a different speed in water, and then it changes it spreads it out. And so that when it spreads out, then we can see all the colors of that rainbow. And something cool about a rainbow is that whatever rainbow you see, no one else will see the exact same rainbow. So whenever you see a rainbow, it's almost like it's your own personal rainbow, because those light particles that are coming from that rainbow are going to hit your eyes, and they won't hit anything else. Once they hit your eyes, then they're done. They stop. So you're going to be the only one to see that specific image of that rainbow. So I always kind of think that's something special. I always try to slow down my day and try to, when I see a rainbow, I just try to think of, I don't know, just how special life can be sometimes. I also see that some people are saying that because some waves, lights bounce off of molecules. All right, that's pretty cool. Particles inside the diffraction with gravity, maybe there's something to do with gravity. It has something to do with waves or something. Why would it be in this segment? Definitely has to do with waves. So I love that you're thinking it has to do with waves. So we have then what we think. So let's get down to the source. The source of this wave was the laser. And when we had this laser, what the purpose of this diffraction grating is to make all right, so like, hold on a minute. All right, guys. Yeah, that was just someone playing around. I think someone was probably playing with I don't think it was a drill or whatever it was, but no. And I'm not getting out of there. If there was a real fire, like, I know. Dude, we get it.
False alarm on the fire alarm. The do not evacuate. It's a false alarm. I apologize for the inconvenience. It was due to construction.
All right.
Thank you so much. Again, this is a false alarm. Thank
All right,
you.
we got you. Okay, so we're bringing it back, So I hope you guys didn't evacuate your house as well. So the purpose of this diffraction grating was really to make two waves from one wave with the same frequency. So what we're seeing here is this diffraction grating had a purpose. And I'm saying it was to make two waves from one with the same frequency. So that's what I'm saying. And so what I'm going to do, I'm going to bring us to a simulation. In this simulation, I can do a lot of different things. I can look at waves, and I can see how a wave looks as it goes through water. I can look at this wave and how it goes through water, but I can also see how waves interact and how they interfere with one another. So as I turn on both of these waters here, they both make waves and they both make these ripples in the water. When these ripples in the water are happening, they're dropping at the same frequency, just like how that diffraction grating made two waves with the same frequency. And as these waves move through the water, that's the medium, then we see that we get these bright spots where there's high waves, and we get these dark spots where there's no waves. And so we see that this thing called interference actually happens. That's where these waves build up and tear down. So as these waves build up, then they interfere with one another and they make these high points in the waves. And so what we did was we had this diffraction grating that kind of is acting like a slit where we make more waves than one. And so this right here is kind of like this diffraction grating, this little thing, this yellow thing, I can move it. And what happens is as the wave hits here, then it gets through this slit and it starts to spread out. This is what diffraction is called. A lot of you have seen it. If you've gone to down to La Jolla and you get to that Seal Cove or whatever it is, and you can see how waves hit the pier or hit something and then it bends around that pier. So we've seen it. And what I'm going to do is I'm going to change it from one slit to two slits. And now what I'm doing is just like how the water dropped and made two droplets at the same frequency. Now I'm getting this one wave to get split up into two. And what I see happening on the other side is this pretty cool thing where I get these bright spots where these waves build up and these dark spots where the waves destroy one another. So that's going to bring us over here to this diffraction. So this diffraction is where I'm going to take this laser, I'm going to turn on the laser. And as I turn on the laser, I can change the diffraction grating. That's what the laser light is passing through. And if I change that, I get a different laser pattern as a result. And if I change the pattern of the diffraction grating, I change the laser pattern as a result. And I can change the square width and I get a different pattern. I can change the circle diameter and I get a different looking pattern. I can change it over to where I have a bunch of dots and I can change the spacing between them. And I get a different looking pattern. I can make from order to disorder, and I can see that the pattern changes as well. I can change the diameter of those circles to be big down to small, and we see a different pattern. So these laser patterns tell us exactly what's going on here and the size of this. So the job I had was looking at these pictures and being able to look at this picture and say, well, I know this, so therefore, the thing I made is only one atom thick. If I saw a pattern that looked kind of like this, then it was only 1 atom thick. If I saw a different pattern like this, then I know it was more than 1 atom thick. So I had to make it so that way I built something that gave me a pattern like this to where I could have it be big or small, and that told me exactly the size of the atom I'm looking at. And you can change the shape of what you're looking at. So the atom sometimes isn't a perfect circle. Most of the time it isn't. And I could change it and see the different looking shapes that could come about from it. So that's what we had here. That's the whole purpose of this wave-particle duality. So, or rather, that's what happens here with this double slit experiment. So with this double slit experiment, it has 1 wave coming in, then it makes 2 waves. Then these waves interfere. And when they interfere, they create bigger waves and smaller waves. And that's why we're able to see these cool patterns. So what I'm going to do now, I'm going to take us over to here. So I'm going to have this Dr. Quantum video. I got a Dr. Quantum video. That's really this Dr. Quantum. He's a really good friend of mine. We go way back, actually. My friend Dr. Quantum, he was my roommate in college. We're really good friends still to this day. Like I was even just talking to him on the phone last night. So what I'm going to have us do is we're going to watch this video from my really good friend, Dr. Quantum. And we're going to take about a couple minutes, and I want you guys to watch it. I'm going to put it into the chat so you can guys watch it in the chat. And then I'm also going to play it here for myself. So that way I'm able to watch it too. So I'm going to put into the chat this video. So this is Dr. Quantum. I want us to watch this, and then we're going to come back and we're going to work on these answers here for numbers 1 through 4.
What they taught us in school isn't really the way it is. And that our senses are playing tricks on us. You just gotta wonder, what is this reality that we find ourselves in? Quantum physics says it's all just waves of information. Do I believe that? I hope so. Yikes! And here we are, the granddaddy of all quantum weirdness, the infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So when we throw things, that is matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits and it goes through neither. And it goes through just one and it goes through just the other. All of these possibilities are in superposition with each other. Physicists were completely baffled by this. So they decided to peek and see which slit actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched.
So this brings us to this thought experiment called Schrodinger's cat. So Schrodinger's cat is where they said, so this cat is either dead or alive when he's in a box. And so if you open the box, then there's this vial in there that will explode and it will kill the cat. And so if you open it, the cat dies. And what you're asked is, well, is the cat dead or alive? But he's inside of a box. And so you have no idea really knowing if he's dead or if he's alive. And so if you try to shake it, then the vial explodes and the cat's automatically dead. If you even just try to peek inside of it, then the vial explodes and the cat is dead. If you try to use x-rays to look inside of it, then this vial explodes and the cat is dead. So basically what it comes down to is if you measure the experiment, if you try to quantify, if you try to look at it, you're affecting the experiment. That's what is being said here. And so that's why when they said, when you look at the electron going through that double slit, then you're deciding it's what it is. You're deciding that the cat would be dead. But until you look in the box, the cat is in both states. It is both alive and dead at the same exact time. And that's one of these crazy things, a crazy thought experiment. So if you want to try to go deeper into a world where it's just crazy to think about, or if you're just have a hatred towards cats, take a look at this Schrodinger's cat thought experiment. So when we shot the marbles from that double slit, and what we classically expect is we expect two bands on the wall. That's where J.J. Abrams got the thought from. So I like that you are using that. So J.J. Abrams, he's a big fan of physics and science and astrophysics. That's why he made a really cool Star Trek movie. But I'm not going to go more into that. So what happens when the two tops of the water waves meet at the double slit, on the double slit? Well, they went through it and they interfere. Not only do they interfere and make a bigger wave. So when we shot little tiny bits of matter as well through the double slit, the electrons made a diffraction pattern just like light. So that electron made a diffraction pattern just like light, which is a wave. But when we looked at the electron, it made the two bands on the wall. So it acted like a particle. So this is what we expected to happen. And this is what happens when we look at the electrons. If we don't look at the electrons as they go into the slits, it makes a diffraction pattern, just like in light. So let's give yourselves here, I'm going to give you guys about 30 seconds to say an electron behaves like a wave or a particle. And I just want you to tell me why. So I'm going to give you guys like 30 seconds to get to that. All right, so let's bring it on back now. It is both. And it's neither. So what we're going to get to now is I want us to get to this hyperphysics site. From this hyperphysics site, we're going to be able to look at this thing called the photoelectric effect. This is the thing that Albert Einstein won his Nobel Prize for, this photoelectric effect. And what it is it's just electrons being ejected from a surface because light hits it. And so in this, it kind of shows light being a particle, because when you increase the intensity of light, the number of the photons are increased, but their energy does not increase. Changing a frequency sometimes made it that way some waves weren't, or some electrons were not ejected. And the electrons get emitted immediately after light hits a surface. So when light hits a surface, it makes electrons move. When electrons move, that's electricity. This is how all solar panels work. Light hits a solar panel, makes electrons move. So what we're seeing is this photoelectric effect really shows that light is also only a particle, because a particle has to hit something and bounce off of one another. If it was a wave, it would interfere with this, and then this electron would then get brighter. But that's not what happens. It ejects it, it bounces off of it. And so we're going to need to write a few things down from this. What we're going to write out all right, I'm just going to figure out a nice way to do this. I'm just going to be copying this one here. Number one, the electrons were emitted immediately. And intensity of light. So I'm going to start writing number one. And I want you to write number one as well. And where you're writing it is here on this backside, where it says hyperphysics. So I want you to get to here and write down words. So number one, I'm saying that electrons were emitted immediately from light. Number two, the photoelectric effect. Light has to be a particle. That's one of the key things. So this is even the number one thing I want us to try to get, that light has to be a particle in order for this photoelectric effect. Photons hit and bounce off of electrons. So now that we have this hyperphysics site, now that we've written down the 3 things we learned from this website, what I want you to do is from the site I just put into our chat, that's where you're going to be looking at this double slit experiment. From this double slit experiment, what I want you to do is you're going to draw in the screen on here. So you're going to go to that site. From that site, and I want you to get to this diffraction pattern over here where you're going to get using these slits. So when you use these slits, what was it? Not yet. Right now, what I'm currently doing is I'm trying to look for the thing I want you to do so we have an understanding of the thing you got to do. All right, so on here, with respect to what you're looking at, this screen and the screen chart are going to follow from that diffraction page. So the screen left, screen chart right, it's going to follow what we see here, where left is going to be screen and right is going to be screen chart. And what I want you to try to do is decide what you have on your screen. And when you have something on your screen, then I want you to draw on your screen chart what happens as a result. So I know here there's a scale with intensity and position, and there's no scale on the screen chart as well. So I want you to try to draw it as best you can. And so all you got to do is draw and draw for these 2 places. So draw for screen and draw for screen chart in these 2 places, and that's going to be what you got to get to for this last part. On that note, do I have any questions here? So no one actually gets it. No one does. And so what I'm also going to do is I'm going to put this video in here for us. Please light this up before you get out of here. Thank you. So no one really understands this. And you can see Neil deGrasse Tyson, he even goes on to say that no one really understands this. And it's okay if you don't. It's tough to understand. So, see, dude? So hopefully you guys got something. Do I have any other questions here? So when you're done doing this assignment, you're going to go back over here to our Unit 1 waves, and this is where you're going to get to our packet pages 9 and 10, the wave versus particle duality. We also have this waves question number 5. So beyond just that, looking at this double slit experiment and the photoelectric effect, we're to use both of these experiments to 1, answer how does light act like a wave, and 2, how does light act like a particle? So we're gonna be looking at both of these experiments, the double slit, photoelectric effect, and you're trying to answer both of those questions. And really you can just say, well, light interferes, and for the photoelectric effect, light interacts. From that Unit 1 waves, where we're turning in our assignment is you go to packet page 9 and 10. You do the click here to make a copy of your assignment. You make the copy, and you're going to take your pictures and insert the pictures of your document into these pages 9 and 10. On that note, I'm going to say thank you guys for coming out. I'm hoping you guys had a good, have a better understanding of this. This is pretty tough to get to. It is pretty confusing stuff, but it confuses physicists even now today. So don't worry if you don't get it, because even Neil deGrasse Tyson, I think one of the most famous living physicists right now, he doesn't have an answer for this. And he even says that he doesn't have an answer. No one on earth does. So we're just learning the effects, and we're seeing that light is a wave and light is a particle. It's not a wave. It's not a particle. It's both. It's neither. That is life. And on that note, I'm going to say thank you and have a great day.